Now I'd like to look at some examples of series where we try and apply this new test for divergence. So first example is the sum from k equals 1 to infinity of -1 to the k. To be clear, we've already looked at this series and we actually showed that it diverged using the definition of convergence and divergence. Here, if I want to try and use the test for divergence, importantly, what we have to do is take the limit of the terms. So in an earlier video, we took the limit of the partial sums using the definition, and that was a different idea. So here I'm looking at the limit of the terms. The limit of the terms does not exist because these terms oscillate back and forth between plus and minus 1. Importantly, does not exist certainly is not saying that they go to 0. So consequently, we can say that this series diverges. And what's going to be important as we start to develop more and more tests is to justify very briefly how you know it diverges. Part of that justification is showing our work and finding the limit, but we also have to say by the test for divergence. Okay, second example, if we consider the sum from 1 to infinity of 3/2 to the k, again, what I would first look at is taking the limit of the terms of this series. And notice that this is 3/2 is larger than 1, and I'm raising it to the kth power. This is going to grow without bound. So we'll get infinity here, which once again, importantly, is not 0. So we can quickly conclude that this series diverges, once again, by the test for divergence. Later, we're going to see that this is an example of what we call a geometric series. And so we'll also have another way to analyze that because of it being a geometric series. And suppose we have 10k squared over k squared plus 3k plus 1, and we're summing that from 1 to infinity. Again, taking the limit of the terms of this series. Notice that I have a degree 2 polynomial on the top as well as on the bottom. So I could then take the ratio of leading coefficients. So the coefficient of k squared on the top is 10, the coefficient of k squared on the bottom is 1. So that means that this limit would be 10 over 1, or 10. So this limit exists and it's finite, but it's not equal to 0. So we still have to remember the context of why we're looking at this limit here. For the test for divergence, even if you get a finite limit, if it's not equal to 0, then again, we can conclude that the series diverges. So this series diverges, and again, it's by the test for divergence. And to tie this back into an earlier idea, the sequence of terms 10k squared over k squared plus 3k plus 1, that sequence converges to 10, but the series diverges. And so being able to really pay attention to what we're taking the limit of in order to come to our different conclusions. The other thing I want to mention, which I will likely mention at a later date as well, somewhat arbitrarily, I've been starting all of my sums at 1. But I want to be clear that you could have these sums start at like k equals 7. That would not in any way affect the way that I would do this test, and it also would not affect the conclusion. So a lot of times, kind of arbitrarily, I write examples that start at k equals 1, but you'll encounter sums that don't start at k equals 1, but you'll see that we're still very much focusing on the general terms. By changing the starting value, we certainly would affect the sum of the series in the instance where it converges, but we're really interested in just does it converge or diverge at this point, especially when we're using this test here. So example 4, if I have the sum from k equals 1 to infinity of k squared divided by 3k cubed plus 1. Then again, I want to take my series terms and take the limit as k approaches infinity. Here, the degree of the bottom is larger than the degree of the top, so we get that that limit is 0. So very, very importantly, I want to point out that when this happens, we get no information from the test for divergence. And this is really important because this is a common misconception. So put this in red. If the limit as k approaches infinity of a sub k is equal to 0, this tells us absolutely nothing about whether or not the sum of the series converges. So this is a really common misconception. We have the statements from when we proved the test for divergence. We had the statement of the test for divergence as well as its contrapositive. This is not equivalent to that statement. So if the terms go to 0, what we're going to see is that the series could converge or it could diverge. So what you absolutely want to avoid is any time where you're saying that because the terms go to 0, the series converges. And this comes back to why I said I like that it's named the test for divergence, because I feel that we would be less likely to say a series converges by the test for divergence, right? So kind of naming in that to really keep in mind, this test is only conclusive if it can show that a series diverges. So what we can think of here is essentially, if you think of the collection of all series where the limit of the terms is 0, basically what happens is a subset of this is convergent series. So they're not equivalent. And we saw before that convergent series must have this property, but it turns out that some diverging series do as well. And in fact, we've seen one example of a series that diverges that happens to have terms that approach 0. So what I want to put here is an example of divergent series such that the limit as k approaches infinity of a sub k is 0. So the one that we've already seen is our telescoping sum with terms natural log of k plus 1 minus natural log of k. So we showed that this telescoping sum diverges. And again, we did that by finding the pattern of the partial sums, and we actually used the definition by taking the limit of the partial sums. But also, what we perhaps didn't look at is if we're looking at the limit of the terms, we get the indeterminate form here of infinity minus infinity. But I can write this as a single log expression. If I take this as log of k plus 1 over k, note that k plus 1 over k will approach 1. So our limit approaches the natural log of 1, which is 0. So the terms of this series do approach 0, but the series still diverges. And another really famous example, which we're going to focus on in a future lecture, is the sum from k equals 1 to infinity of 1 over k. This is what we call the harmonic series. And this is going to become very easy to see when we have a future test. So I'm going to hold off on that. But you can certainly see that the terms go to 0, the 1 over k. But we will prove that it diverges later. In particular, once we talk about the integral test for series, we'll be able to confirm that the series diverges. And even though we haven't shown that it diverges yet, this is a really good series to keep in mind because, like I said, a lot of people mistakenly think that if the terms go to 0, that the series converges. And if you have a good counterexample in mind, you'll be less likely to make that mistake. So thinking about either of these, but we'll see the harmonic series is really a good counterexample for a lot of misconceptions. So just trying to keep that in mind so we don't end up making the statement that terms going to 0 would in any way imply that a series converges. So I'll point out, going back to this last example, number 4 here, at this point, all that's expected is that you can identify the cases where this particular test is inconclusive. Once we start to learn more tests, essentially, it's not a bad idea to try the test for divergence at first, because among our collection of tests, we're going to find that this one is maybe one of the easiest to actually use. But if you ever encounter a situation where the terms go to 0, know that you then have to move on to another test. So right now, we don't really have any others to move on to, but we'll start to develop those. And just kind of remembering that we can't stop with this test if the terms go to 0.